Well, we've just analyzed the relationship for water in its gas phase going to water in its liquid phase. But it turns out that the phase exchange involved in converting water from a solid to a liquid to a gas by adding heat to it has profound implications for the climate, because, as we'll see, it takes extremely small amounts of energy to convert ice to liquid water, that is, to melt ice. But it requires a massive amount of energy to convert liquid to gas phase water. And so let's look at some possibilities. Let's plot on the horizontal axis the heat required to execute changes in phase of water, and we're going to start with ice. And we're going to use 1 kilogram of ice to represent this so that we can write the absolute amount of heat required to execute these transformations. And on the vertical axis, we're going to plot temperature. So temperature can define these transition points where we have, first of all, the melting of ice to form water, and then the increase in temperature of that water until we finally reach the point where we vaporize that 1 kilogram mass that was originally ice. So let's take a look at this. The amount of heat required to convert ice from minus 40 degrees Celsius to its melting point at 0, that's this small increment of heat in the far left-hand side. Very small amount of energy required to do that. But now, when we convert that solid phase of ice to water, that also takes a very small amount of energy. And you can see why that is, because water is highly polar, and those water molecules are moving past, sliding past one another in the liquid phase. But when we form the solid bond, the crystal structure of water, there's a very small difference between that phase, the liquid phase, and the solid phase, represented by the crystallization that creates the ice structure that we know so well. Now, when we proceed along adding more and more heat, we take the liquid water and we warm the liquid water up to the point where it boils. And we know that that's 100 degrees on the Celsius scale. So then comes the surprising fact, and that is that when we add heat to convert water to steam, it takes a massive amount of heat in order to break the bonds between the liquid phase of water and the free molecules that constitute the gas phase of water. Look at the huge amount of heat required to actually execute that phase transformation. So let's just look at a few questions here to clarify. Let's just make it clear that delta H of fusion is equal to the energy required to melt ice. And you say, well, fusion means bringing together, and you've just said the energy required to melt ice. Well, heat of fusion is the energy that must be put in to break the bonds to form the liquid from the solid, but it's also identically equal to the energy that must be extracted to convert the liquid to the solid phase. Now, in sharp contrast, delta H of vaporization is equal to the energy required to convert liquid water to gas phase water. Now we're ready to take a look at these different possibilities. The enthalpy of vaporization of water is a seventh the enthalpy of fusion. Well, we've just deduced the fact that the heat required for this same 1 kilogram to convert from liquid to gas phase is much, much greater than the enthalpy of fusion, so that's incorrect. Next possibility, the enthalpy of vaporization of water is about half the enthalpy of fusion. That's clearly incorrect, too. The sign is even incorrect. The enthalpy of vaporization of water is about the same as the enthalpy of fusion. They're highly unequal, and we can see that because this is the heat required to convert solid to liquid, and this is the heat required to convert the liquid to the gas phase. The enthalpy of vaporization of water is 2 times the enthalpy of fusion. That's wrong. The enthalpy of vaporization of water is 7 times the enthalpy of fusion. That's correct. But this plays into the climate system in a very, very important way, because it says that the heat required to melt the Arctic ice cap is very, very small. And so it is. And as we've seen, the Arctic ice cap is rapidly disappearing. We've lost 75 to 80% of the volume of permanent floating ice in the Arctic in just the last 35 years. So ice is extremely delicate thermodynamically, and yet the ice that exists in the Arctic is fundamental to setting the climate structure as we know it today. If we lost, as we are, the permanent floating ice in the Arctic, it will have a major impact on the overall dynamics of the climate structure. But then let's look at the energy required to convert water to steam or water to the gas phase. That is a gigantic amount of energy, which means that storm systems, which are driven entirely by the conversion of gas phase water to liquid phase water, release a mammoth amount of energy when they do it. A hurricane is a good example. Also, a large storm, just a typical storm that we have, for example, releases 10 times as much energy as the energy contained in an atom bomb. A hurricane contains 6 orders of magnitude, 1,000,000 times the energy of an atomic bomb. And the violence that's released in those large storm systems is a very important part of the changing climate system. It's why storms are becoming much more violent, much more frequent, and much more destructive. It all comes back to the thermodynamics of water.